I've submitted some bio of me on the page, but what you really want to know is that I was paying maybe with software programming for 15 years now, and now I'm working at IBM Research Center and in Krakow. All right, lockless. What does it really mean, lockless programming? Of course, yeah, no logs, right? But that's kind of a silly answer. So lockless programming is programming with multiple threads that access shared memory, and threads cannot block each other. There's no possibility, or should there be no possibility to any thread to not do anything, just wait. They should be all working hard with what we're paying them for. Why? Why should we do it? Let's consider a single path of execution. We've got some code, we've got some critical section. Well, critical section with single thread on single CPU is silly, so let's add another one. And when they both try to enter it, they can't. One of them has to wait. Doesn't seem that bad until you start adding more and more threads running on separate CPU cores. They're not sharing pipelines. They're not sharing any processing unit. They're completely separate, but they operate on shared memory. So the more cores you have, the bigger the problem gets. Threads are not doing anything. You're wasting your hardware. There's some problems with logs. Everybody knows dead logs, live logs, priority inversion. It's when the low priority thread holds a log and high priority thread can do nothing about it. Even if the scheduler gets the CPU time for this thread, it can do nothing. It has to wait for the log. Long convoy is similar thing when a thread holding a log is scheduled off the CPU, and the log goes with it. Also, the non-blocking thing is very important for real-time applications, like game programmings. Okay, how do we do it? There are two building blocks of lockless programming: atomic operations and memory barriers. Atomic, of course, are indivisible. They consider being done in one step. The two basic types of atomic operations, CAS, compare and swap, and FAA or AFF, fetch and add, or add and fetch. They're really very similar. They're grouped in this one. And as per memory barriers, 4 basic types: load, 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 store, store, load, store, store. I get to these later. Compare and swap. This is some pseudocode what compare and swap is supposed to do. It takes a value, a variable to change, an old value of the variable that we expect it to have, and a new value we want it to be set to. And if the variable has the old value, replace it with new and report success. And if not, report failure. And this happens atomically. So it cannot be interrupted by any other thread, and usually is supported by a CPU. It always is. It's not usually. Fetch and end is very simple. Hold the value for a second, add the number we passed to it, and return the old value. Add and fetch is very similar, but we first add and then return the value. And it cannot be interrupted by any thread as well. As per barriers, we need to introduce the notion of sequential consistency. What is sequential consistency? Let's consider this pseudo-assembly with logs. We create a log, we do some reading variables into the CPU register, we do some operations on them, we store them in some order. And this is what a programmer intended to do. Read X, read Y, do something, store Y, store Z, store X. But there is such a thing as reordering. A compiler can reorder your instructions, a CPU can reorder your instructions and will reorder. A JVM, if you're running on Java platform, will reorder your instructions, and what would probably happen is that all those operations, read and stores, will be a completely different order than you intended to. If you have logs, that's not really a problem, because nobody can interrupt you, nobody can do anything else with those variables if they're in the critical section. But What if you don't have locks and you're running more than one thread? And they're on separate CPUs, they can really run in parallel. If you see those operations ordered in the order that you are not completely not aware of, because compiler and CPU at JVM are doing their things, what are actually values of X and Y? You don't know. You have no way of knowing that. And sequential consistency is when all the threads on all the CPUs agree on order that memory operations happened. And that order is consistent with what you, as a programmer, intended. As simple as that. So to attain sequential consistency, because you really want to know what happens in your code usually, we use something like memory barriers. Memory barriers is a very low-level thing that's supported by CPUs. And they go like this. A load barrier means no reads that happen before the barrier can be reordered after the barrier. So we have read X and barrier and read Y. Neither compiler nor JVM nor CPU are allowed to reorder them. The stores can be ordered, can move across the barrier or thing, but reads are always the same order you intended. Store barrier is the same for stores. They cannot be reordered no matter what. Load store barrier, as you probably already realize, is that no reads can cross the barrier and no stores can cross the barrier, but they're separated by the barrier. Reads are before the barrier, stores are after the barrier, cannot be reordered. Of course, all the reads can be ordered before they reach the barrier, and all the stores can as well be ordered after the barrier. And store load barriers similar, but stores happen before the barrier. There's a thing called full barrier, which is what usually is used. It combines all the four. This means no reordering can happen across the barrier. All right, this is very dry and maybe not that interesting, but let's get practical. Let's write some lockless code, a shared data structure, a FIFO queue. It's not mine, as was designed by one John D. Valois. You can Google the paper he published on this queue. So let's first consider a queue. This is what he proposed. We have a head, a tail, and marker, which is a kind of node that only exists so that head and tail are not null. And if we use logs, the in-queue operation is very easy. Acquire log, create a new node. Tail of the queue starts pointing to our new node, and the former queue points to the newly created element, and then release the log. Easy. If we get rid of the logs, then we can find problems. Do you know what operations here are susceptible to being interrupted by another thread and are dangerous? Does anybody know? Those two. We create a new. The queue is thread local for us, so we don't care. But tail, next, and tail, writing to those variables can be interrupted by other threads, and it will lead to inconsistency. So what John Valois proposed is this operation. We create a new node as previously, the first 3 lines, and then we do so-called CAS loop, or compare and swap loop. We take a temporary variable, assign it to point to tail, and we try to replace the tail with our new node. So if the last element next was null, then we replace it with our newly created node. When it succeeded, then we just exit and do something else. But I'll get back in a second. If it don't succeed, we do something weird. Do you know why this thing here is necessary? Okay, so first let's say about that. Replace a tail that pointed to our temporary variable to a new element that is supposed to be a tail. And we do it atomically as well. And it can fail and we don't care. You know why? All right, let's consider that this code is executed by 2 threads. And any thread can be scheduled off the CPU at any time, and we don't have any control over that. And at any moment, the state of the queue must be consistent. Let me actually go show this. So this thing is important because we need to point the tail to a newly created node. But the thread that does that can stop here, and then another thread on another CPU can do the same operation, enqueue another element. And so the tail is not the old tail is already somewhere in the queue, in the middle of the queue. So the P that was a true tail is not tail anymore. So we cannot just assign it to tail. We just need to assign it only if it was not assigned previously. If it was, it doesn't matter. If somebody else succeeded with that, that means it added a true tail to the queue, and we're done with that. But if you have a thread that's stopped here, another thread that's stopped here, replace the tail with something else, and got third thread running through this loop, and seeing a tail that was valid, like where's this tail? It points to a marker. It's really inconsistent with what the queue points now, but the true tail has not been updated because the threads that should do that are of the CPU are descheduled. The system schedule doesn't like us. It was written by our worst enemy, and is throwing wrenches in our code. So this poor thread that tries to find a true tail must update the whole queue. That's why we need this CAS. It's tricky. If you want to really understand that, you should probably play with that code. Try to write an implementation without that condition. Run it for 5 million times on all the cores of your CPUs and see how it fails. Dequeue operation, way simpler. Or maybe let me go back and try to summarize this in plain English. The whole loop tries to find the true tail of the queue, right? If we can't do this, we're not on the true tail because somebody changed it in the meantime, and we need to update the whole queue for it to be consistent again. And we succeed. We just leave the code. Okay, dequeuing. Simpler but tricky as well. We try to the true head, if the queue is empty, which is shown on this picture, it has a single node, and the node's next point to null. This is how we see this, the queue is empty, and this is what the code does here. If it's empty, right? Error or return queue empty, whatever. We try to replace head with the thing, if it's the thing we think it is, with its subsequent element, with p next. If it doesn't succeed, that means somebody changed the queue while we were thinking about it, somewhere in that loop. So we need to do it again and again and again until I succeed or queue is empty, and then return the value that was held in the element. Any questions to that? Hardcore stuff. OK, so this implementation, any thread, all the threads do some work. They never wait on each other. They never block. They still control their own destiny. And they, if we want these, there is a potentially infinite loop, but we have full control over it. If we want to algorithm to fail after, let's say, 5 tries to enqueue, we can just encode it and be done with that. Okay, so is it silver bullet? Does it solve all the problems we have with multi-core programming? Not really. Analyzing this code is very more difficult. Creating an algorithm that, or a shared data structure that works without locking is much more difficult than with mutexes or critical sections or whatever. And also, there's something, an ABA problem that is specific to lockless programming. So let's consider a stack. This is a stack, simple implementation of the stack. Top element, A, B, C, some items put on the stack, and this is how the operation of popping of the stack works. We read a first element, we read the next element of the first, and we replace top with the pointer to that. So let's have one thread doing that, and another thread doing other weird things. And the third thread was able to execute first two instructions. He knows what the top is, A, he knows what the next element, B, is, and then it gets the scheduled. And the other threads do a lot of things in the meantime. He pops first element, pops the second element, and then pushes the first element back. So at the end, instead of stack being A, B, C, it's A and C. And the poor first thread tries to do this. And it is, if the top is A, replace it with B. The top is A, right? The top points to node A, so it's replaced with B, which leaves the whole stack inconsistent. It really shouldn't happen because that's not what we intended. So how do we deal with that? Tag references, intermediate nodes, and LLSC. Tagged reference is a kind of reference to a variable, but with a tag attached. So if we create another reference to the same object, we tag it with a different tag, different etiquette, different label, so that cannot be confused with one another. Intermediate nodes is a technique a memory extensive technique to add another node between data nodes. Only for the reason that they're different from each other. They're always different. They cannot be the same. And LLSC is, again, low-level instructions supported by some processors. Load, link, and store conditional. It separates the notion of storage has a value from storage has changed. It's unfortunately not supported on x86. But is in PowerPC, ARM, and some other processors, or MIPS family. So load link is very, very simple. Read data from memory and mark it. Very simple. Store conditional, if the memory location you want to put your data to is marked, then do it. You can freely store the data and then unmark the memory location. And report success. This is done atomically. If somebody else has written in this memory location before our poor thread could do that, then the location isn't marked anymore, and the store conditional returns failure. Any questions? No. OK. How do you use it? How do you actually can use this in your day-to-day job? C or GCC actually has so-called GCC intrinsics. One of them are sync, fetch, and add, sync, add, and fetch. They're simply fetch and add operations. Bool comparent swap and val comparent swap. They don't decide. They used to implement CAS loop. Bool reports success or failure. Val returns the old value if the operation failed and new if succeeded, or the other way around. I don't remember. And sync synchronizes a full memory barrier. GCC does not give us access to other memory barriers. If we want to do that, we need to get down to assembly. C++, standard 11 or 2011 has include so that atomic namespace, no, include a functionality, and it defines an atomic template. An atomic template can hold pretty much anything. So any simple data structures like ints, characters, longs, doubles, etc. It can hold references to objects, can hold pointers, so anything you need. And it has store, load, which are pretty obvious. And compare and exchange does CAS, and fetch add for numerical types does just that. And also atomic thread fence is used to set a memory barrier, and there are the function takes argument which allows us to specify what memory barriers we want, but the names are really different from the usual low-load store, so you need to map pretty much on your own or read into the documentation. Java has, since I guess 1.5 or 1.6, Java utility concurrent atomic, has atomic integer, atomic long, and other numerical times, which add and get and add are fetch and add operations, compare and set, pretty simple. Atomic reference is used to hold a reference to another object, and Java has a nice thing called atomic stamped reference. And this is used to do this. The atomic stamped reference hold the reference to an object along with a stamp, they call it, a end value that uniquely identifies our reference. It also atomic marked reference, where the stamp is not int but a bit value. Okay, I think I'm pretty much done. Any questions to that? I can see you guys.
Regarding weight-free programming, do you have experience with true weight-free programming, and any opinions about that?
Yes, I do, and yes, I do. You should really consider not doing that first. It makes your hair gray trying to debug it. Or even seeing the problem sometimes takes ages. And your problem domain must be really one of that you cannot do any other way. I do some low-level programming close to the hardware, where we are employing 12, 20 cores to do something, to do some processing, and all the cores must operate on peak performance. So we cannot have them wait on anything. They must do their thing or abort the operation and pick up another. But once I thought that programming with log was difficult, I don't anymore. It's very, very trivial comparing to that. Does that answer your question?
More or less.
If you have any more specific questions, go ahead.
Do you have any examples of real life something maybe more something different than a queue that you encountered or worked on that would require lockless stuff?
Priority queues, but this is kind of GT grind. In practice, I only do the very simple data structures. FIFO queues, priority queues, stacks, and I'll be needing a tree soon. But I haven't started implementing that yet.
Did you do maybe some work on scheduling stuff?
No.
Maybe? Thanks.
Any other questions?
Okay. Hello.
Hello.
I saw one implicit lock there in your solution. Let's take the example. I have 4 threads, workload with, for example, 1,000 elements for each thread, and they are building some BQ. And in your example, you're making a do-while operation when you check the cache results.
Right. NQ or DQ? Let me go back to the code.
Mm-hmm.
Can I have the slide again?
Mm-hmm. And I see one implicit queue because there's 4 threads. I can fight for this. Will still be very often in this error block.
You're talking about this part?
Yes. Mm-hmm.
So
and the workload is very big. I think it will be the problem. This will be implicit lock.
If you have a thread that is slower than all the other threads, that yes. It depends actually on scheduler. If all threads are equal priority and operating on equal hardware, but this is pretty much the case. And the scheduler is not angry with you for your behavior, that should not happen.
Okay,
and pretty much won't ever.
Okay, maybe I will try at home to make debugging and see how many times it go to this failure. But
Okay.
I think it could be, you know, I think that 60 or 70% calls can get there.
From what I measured, it's close to 0%. It's 1 or 2.
Okay.
Because I had the same concern, and I did some thinking first, drawing diagrams, thinking hard about it, and then I actually get down to the code and measured it.
Okay, thank you.
The hard thing is that when you measure it, you skew the result, because any measuring here is very costly compared to CAS. Be mindful of that.
Any other questions?
Have you measured how much better throughput you get using non-blocking queue instead of using standard implementation?
3 times.
And how much
Granted that my problem is very, very specific.
Mm-hmm.
I got very short burst of activity in processing, and then I pass some data to another parts of the system.
Okay. And
So
how many cores?
24.
24 cores. Okay.
Yeah, so it's significant.
Yeah. Okay, thanks.
Any other questions? Okay, if not, thank you very much for your
Thank you.
lecture.